Lower. Mic sensitivity a little bit. Is that better? Less sensitive? Okay. Okay, now we can actually do math. If you go to our page, and we will get to improper integrals later in class. So I'll ask you if you guys have questions about the videos. By the way, I did put the complete YouTube playlist of videos I made for Math 1700. So you might want to take a look at this. What I said is that a lot of it is stuff that just introduces integration. So we're skipping over a lot of the early ones. But for example, the derivative practice and antiderivative practice we did I work through them in these videos right here. The one we did like the first Friday. And so you might want to look at that. I don't have any videos on U substitution somehow. I must have just taught it. But I do have some videos on integration by parts. You could also look at, which we're going to get to. So, okay, so you might want to look at that. And I might assign, and like the videos I assigned for today, for example, are on this list also, like, you know, improper integrals and stuff. So, okay. And then the other thing then is I actually uploaded a completed, well, let me download the lab so we can look at it, the PDF. Oh, I'm not sharing screen. Bad. Screen. Okay, so here's the lab we were looking at. And I also put up a filled out Mathematica notebook. I just posted this. So let's see. Because this is what I can walk us through basically. Yeah, and yeah, so here's the lab and then here's, so I guess what I would want to say is that what we were doing, if you remember in lab, was we were trying to approximate that integral that's on the screen right there, the integral from 1 to 10, 1 over x. But we were trying to approximate it sort of numerically, right? I mean, but we can actually figure out exactly what it equals. If you remember. The stuff we need to get our brains back in gear to do this, but right, like, so okay, so what we were doing was lab to estimate the integral from 1 to 10, 1 over x dx. And later in the lab, there's another function. But if you think about it, what does this equal, right? What's the antiderivative of 1 over x? ln, right? It's the natural log of x evaluated from 1 to 10, which is natural log of 10 minus natural log of 1. What's natural log of 1? Yeah, why? Why is natural log of 1? Why is natural log of 1 equals 0? Yeah. Right, so ln of x equals y means e to the y equals x, right? It's kind of the definition of natural log. And so ln of 1 is the power you raise e2 to get 1. So y equals 0. Okay, just a reminder. Natural log of 1 is 0. So this actually just works out to be natural log of 10, which if you ask a computer, it's about 2.3 something, right? Let's even just ask the Google search bar. Hello. Those are. It's about 2.30258. Okay. Or 585 maybe. So I don't round. Probably I should put 259 if I didn't add another digit. Okay, and then but what we so what I did, there was some stuff in here about reminders, there's some stuff in here about variables, setting variables. So let me go to this notebook and let me just make sure A is 1, B is 10, and f of x is 1 over x. By the way, notice how the x's are blue, like this x is blue down here before I run this. After I run it, it's still blue. What am I saying? The A, I think the A, if I clear, or wait, did I just say A when I meant B? Yeah. I think if I clear the value of B, then this f of B is blue right there. You guys see that? And so but once I actually set B equal to 10, right, so if I ran f of B right now, it's big enough. Should I make this even bigger? It's crazy big. So if I ran f of B right now, it would just tell me 1 over B. But when I actually run B equals 10, it's so sensitive. B was now not blue anymore, and it knows it's 1/10. There was stuff about summations in Mathematica. And then we actually had these formulas for the left sum and the right sum, right? Let me run these and make sure they're good. Okay, and then I said, and then on the lab it says, right, it says, write and evaluate left of 3, like the left sum with 3 rectangles and the right sum with 3 rectangles by hand. So what did I mean by hand? I meant you could actually do this, right? Like the left sum with 3 rectangles, you could actually draw the graph of 1 over x. It looks like that from 1 to 10. There's 1, there's 10. And I could actually say, well, if I'm going to break this up into 3 rectangles, right? I'm breaking this up into 3 intervals. The width is 9, so it's pretty clear that the width of each subinterval is 3. So this becomes 4 and 7. And then if I want to do a left Riemann sum, I would be drawing these rectangles. And so the left of 3 would be base times height of these 3 rectangles. So, or height times base, I guess. So the height, this height is 1 over 1. This height is 1 over 4. And this height is 1 over 7, because this function is 1 over x. And so this would just be, the first rectangle would be 1 times 3. The second rectangle would be 1/4 times 3. And the third rectangle would be 1/7 times 3. Height times base. Is that right? And so that works out to be some number of 28ths. 7, 28ths, 4, 28ths, 11, 28ths, 39, 28. 3 times 39 over 28 is 117 over 28, which is approximately, well, let me ask Mathematica. Numerical value of 117 over 28. 4.178. and when you do this, you get 4.17857. When you actually just ask Mathematica to do it for you, it's the same thing. Okay, so when I said by hand, that's what I meant. Like you can actually do, for a small number of rectangles, you can write these out. All right. What did I just say? 17857. Any questions about that? Okay, I added this thing here. It turns out this is kind of a cool thing that I was going to show you in a later lab, but I want to put it in here. Wolfram Alpha is natural language commands, right? If you go to wolframalpha.com, how many people have used Wolfram Alpha before? Just a few of you, but it's, if I go to wolframalpha.com, it's this calculator. It actually can do all sorts of crazy, you know, if you want to know, like, hey, tell me about facts about Galileo. It will, I guess, give you some facts about Galileo. Which is kind of ridiculous. But if you want to just like do math, there's all sorts of math you can do. And it will integrate things for you. Like if you want to integrate x squared sine of x cubed, go away. It'll give you an answer. It also has a step-by-step solution, except I think, you have to have Wolfram Pro. You have to subscribe, you have to pay for it. But in Mathematica, you don't. In Mathematica, you can actually use Wolfram Alpha. So if I wanted to actually, so what I'll say is, yeah, like, let me copy this, go back to Mathematica. So I says you type the equal sign twice at the beginning of a cell and it makes this orange star, which is basically Wolfram Alpha input. And then I do this, and then I hit Shift Enter. And it will actually give you Wolfram Alpha output. So it'll look like the output here. So it gives you this, but now it's loading. I think it's loading. So it gives you all sorts of information that may or may not be like that you may or may not care about. But now, if you want the step-by-step solution, it will tell you, I think. This may be reason enough to put Wolfram Alpha on your, to put Mathematica on your computer. Take the integral. This is one way to do it. I don't know if this is how I would have done it. But it'll tell you step by step. It's not always the best, most like thoughtful way. But it even tells you like integrate by parts. So that's crazy. It gives you all the steps of integration if you want. All the way until you get the final answer. This is, we're basically offloading our brains onto the cloud, right? Okay, so there's that. That was an example, but here I actually said, and it took me a while to figure out the wording. I tried like Riemann sum for this function, left Riemann sum, and it didn't like it. I said 3 rectangles didn't like me, but I went to look at examples on their website, and it looks like this language is good. So if I run this now, why does that look different? On my computer, my office would look different. Let's see. Anyways, if I run this language, integrate 1 over x from 1 to 10 with left endpoint method with 3 intervals. There's that result again. They actually give you it, like if you wrote out the symbol, you could actually show that this would be the Riemann sum. It might be worth, they're using n as their index. But here, they actually even show you the picture. That picture I just drew, basically. So that's kind of cool. And you can do it, and they give you the error, which we're going to look at in a second. And they actually give you the result with a bunch of different of these rules and much more stuff. But if I wanted like, I don't know, 20 intervals, oops, 320. I thought once I got it to actually give me like a dragger that I could like change the number of rectangles and stuff, but I don't remember how I did that. But like, there you go, there's 20 rectangles now. So you can actually really see Riemann sums nicely from this. So it's worth, you know, I would have a hard time getting Mathematica to plot something like this, but it just gives it to you immediately. So anyways, this is just a very cool aspect of Mathematica now that you can do these natural language commands. Of course, you have to almost go to the website and look at, if anything's complicated at all, you have to go to the website and look and see what language you should use, because apparently they don't say Riemann sum, they say left endpoint method. Okay, so you can get all this. You can do the same thing with the right endpoints. The right endpoint by hand would be the same thing, but with the rectangles, you know, they would be the rectangles like, I don't want to draw on this, but it would be like that and like that and like that, right? You'd have the right endpoint rectangles. Okay, and then I guess what I asked you to do was to start, if you use more rectangles, and remember the exact value we're looking for is this. So with 3 rectangles was not a very good approximation. We got 4 point something. That's because there's all this overlap, right? But with 25 rectangles, it's a little bit better. Still not fantastic. And then I had, I think, let's see, back to the file. So, right, so there's also a thing here that like, I guess there's some general comments I wanted to make about numerical integration. So like in number 6, for example, it asks whether you think the left approximation or right approximation will be, you can see it here. This is an overestimate, right? But there's some general facts about, so let me just, remembering to pause the share so if someone's watching this later or. Okay, so some general facts about Riemann sum approximations. The first thing I would say is if f of x is decreasing, if it's going down, right? Sort of like we can tell if this function goes up and down, then it's a little bit harder to tell what's going on with the left and right sum. But since this is going down, the left sum is going to be definitely an overestimate, right? Because the top left of each rectangle is peeking out over the graph. So if f of x is decreasing, the left sum is an overestimate. And the right sum is an underestimate. Right, but what if f of x is increasing? And I could say instead, I could say f prime is less than 0 or something like that. I think it's on the interval in question. There's functions that go up and down, but if you're doing it on a subinterval where it's always going down or something, your f prime would be positive. Then the left sum, so if this was going up, what would happen? If the function was going up through this point, this left rectangle would be what kind of under or over? Under, right? You can see me moving my hand. Pretty clear. Left in is an underestimate. And the right in is an overestimate. I'm just using this shorthand for the Riemann sum. Okay, so those are some general things to keep in mind. And then, all right, back to the file. Numerical value using the integrate command was right there. So that's the, yeah, that agree. This number should agree with the natural log of 10 that we found earlier, right? It's the exact value. And then I said, okay, run commands to fill in the table in number 8. So number 8, I had wanted you to actually do the left sum and the right sum for more and more rectangles. So they should be better and better approximations, right? So with 100 left and right gave me these two numbers. Again, they were on either side of 2.3025. 1,000 rectangles are getting closer. 5,000 rectangles are getting even, 5,000 rectangles are getting even closer. 10,000 rectangles, we're definitely getting close. But actually, I'm a little disappointed that this is only like 5-digit accuracy. Or it's only 4-digit accuracy. 2.302. That's not even 4 digits, what am I saying? 3-digit accuracy, I said 5-digit accuracy, that's important. It only giving you, with 10,000 rectangles, you're only getting 3-digit accuracy of the actual answer. It's a little bit sad. So that's the first thing, is like left and right Riemann sums, because you have those little things peeking over the graph, even if there's a lot of them, sometimes it adds up to a decent amount of error. Okay. And then I said plot, you can just plot the estimates for different numbers of rectangles. So the horizontal graph here is like the number of rectangles you're using. And then it's actually plotting the left sum for that rectangle, the right sum, and then the actual values in the middle. And I think I asked on the handout, like, which is which. And then but then I forgot I discovered when I was making that video that you could actually just have it like tell you which is which if you wanted to, using this plot legend. So actually here, you can actually see that the blue dots are the left sum. But we would have seen that anyways, right? Because we knew the blue dots, we knew the left sum was the overestimate. The overestimate's coming down towards, the green in the middle is the actual value. The blue dots coming down from above are the left sum for more and more rectangles. The orange coming up from below are the right sum for more and more rectangles. And they are starting to converge on the correct value, right? Okay. You can actually explicitly compute the error. Did I run the left and right? Let me actually, sorry, I'm gonna go back up here and just run these commands that I never ran. Sorry, that's super annoying. This was the left sum. Maybe I did run. This is the right sum. Oh, I must have run them because I ran, well, okay. Never mind. Okay, sorry, let me go back down here. So, right, we did this plot. And if I wanted to now have the error, this is just the absolute value of the difference between the actual value and the left sum. I'm doing absolute value just to get because it could be positive or negative error, right? This is the right sum. Is this gonna work? Yeah, okay. So then for 500 rectangles, you can see what the error is. I think there was a question on here which was like, how many rectangles do you need to get within 0.001? So like, yeah, so this is the error. These are the errors, right? Find the smallest n to the nearest 10 such that the error in the approximation is less than 0.001. So it's kind of fun to play, just put different numbers in here until you can make this less than, if I do like 3,000, still bigger than 0.001. If I do 5,000, it's less. If I do 4,000 rectangles. So anyways, it's silly to watch me play with this. Okay, so that's all that stuff. I want to get into the trapezoid and midpoint sums a little more carefully. So that's actually kind of one of the reasons I wanted to walk through this together, is to talk about these a little bit before. I think you have homework on this due Friday, so I wanted to actually talk about trapezoid and midpoint sums a little more. So let me talk a little bit about them, and especially like where this formula comes from for the midpoint sum. I talked briefly, I think, in class Wednesday about it, but okay, so let's just say the trapezoid sum. We talked about that, but I do want to draw pictures too, because there's also facts that are similar to those that we can talk about, whether the trapezoid or midpoints are overestimates or underestimates. So if I draw a picture of something let's say that's a graph that looks like this. And let me just draw like one rectangle, just kind of really, just to show you. I think I drew something like this maybe in class Wednesday, you might have in your notes. But this would be like one trapezoid. This is a trapezoid. Right? Versus, let me actually draw the midpoint. Let me actually do over here the midpoint sum. Let me try to draw kind of a big picture again, same picture. But I want to draw a midpoint rectangle. That's reasonably close to what I had before. Yellow. So if I take about the same width of an interval, I think notability would be helpful because I could just copy and paste over. And so we take the midpoint, right? This is the midpoint of the interval. And so if I did one rectangle, it would look like that. Is that actually the midpoint? Close enough. Okay, that would be a midpoint rectangle. But one thing I mentioned very briefly in class Wednesday before we went in the lab was that you can do something, you can do some surgery on this. So let's say it goes to this point. If I draw the tangent line right here, so this is just some function. These are both just the same, just some function. This is like a t sub I, and this is like a t sub I plus 1, right? Just like 2 points that we've broken it up into. So that's what a typical trapezoid would look like. This is what a typical midpoint rectangle would look like. But if I happen to draw this tangent line, then you can see something kind of interesting here. If I look at this triangle and this triangle, the picture is not very good because they don't look the same size, but they are actually the same. Do you believe those are the same size triangle? So in fact, there's a different trapezoid that has the same area as this yellow rectangle. If I think of this as a hinge and I flip this triangle up on top, then, right, there's actually, let me draw the picture even a third time. So these are verses, these are different. This will be the same. If I draw this picture a third time, and use blue, I guess. If this is my interval, let me draw this tangent line again. I promise not going to look exactly the same. Oh, it's so not the same. It's so sad. I want this to be a direct copy of that. But I now have something like this. And this blue trapezoid has the same area as that yellow rectangle, because I've just done some surgery and moved this piece up here. Okay, so these are the same area. Okay. And the reason I'm doing this is because this, now you can tell, like, is this an overestimate or an underestimate? Over. But if I just drew this yellow rectangle, it wouldn't be obvious whether this was an over or underestimate, because some's overlap and some's underlap. But if I do this thing where I move this piece over here, now it's more clear, right? This is an over or underestimate. Under. And so this actually has to do with the concavity of the graph. not whether it's going up or down, but because it's like concave up. Right, so again, I can write down some general facts that if f of x is concave up, the trapezoid sum is an overestimate and the midpoint sum is an underestimate. So just try to fit some of this here. So more, so 3, if f of x is concave up, that's really the second derivative is positive. Trapezoid sum is overestimate. And the midpoint sum is an underestimate. Maybe now, maybe rather than me drawing on the board, you guys should try to draw something similar picture to this, but with a concave down picture. And in fact, I mean, you can probably just kind of see what's going to happen, right? If you had something concave down going through these 2 points instead, it would look like, let me see my finger, I want to move my fingers. It would look like that, right? Concave down. And so now trapezoid would be an underestimate. But the midpoint, the tangent line you get would be an overestimate. So let me go ahead and just write, sorry, hopefully you're finding room in your notes. Write this, if f of x is concave down, and here it doesn't actually matter whether this is increasing or if this is increasing but concave up, it would still be, the trapezoid would still be an overlap. You make yourself, you basically mirror reflected this picture this way. So f of x is concave down, the trapezoid sum is now under. And I can't just remember these, I have to draw the picture for myself. Or at least try to picture it in my head. I wouldn't say memorize these as facts, I would say just understand from where they come from the pictures. Okay. But that's the nice little surgery you have to do to really believe the midpoint, whether that's an underestimate or overestimate. Questions about anything I just did? I do have to give you a sense of where this midpoint formula comes from also, but I'll do that in a second. We could do the Wolfram alpha thing. Did I do that down here somewhere? No. Where's my Wolfram alpha command? There it is. So if I actually did, you could just change this to trapezoid rule or midpoint rule. Go up here and do this again. So instead of left endpoint method, if I say trapezoid method, actually, let me do with 3. So running, yeah, trapezoid rule, 3 intervals, it gives you, I don't actually know why this did the same thing when I tried it. It's like this trapezoid's cut off for some reason. I don't know why you can't see it, but it feels like this should extend up to there and touch. Right? But there's the trapezoids. Again, I'm not sure why it doesn't look nice, but that's the trapezoid rule. You could do the midpoint method. And it will tell you, it will show you, again, just with 3 intervals. Yeah, that's the midpoint method. And again, it's like the idea that somehow this overlap right here is less than this underlap. Again, I'm still not sure if underlap's a word, but because of the concavity of the graph, like this piece that sticks up is smaller than this piece here. Does that make sense? Okay. Now you can actually do, maybe I'll come back to like the formula and why the formula for the midpoint, I think I gave it here. And it looks pretty terrifying or terrible, but I'll come back to that. But then the over-under thing is really just from the fact, so our graph that we're looking at for 1 over x, is that concave up or concave down? It's concave up, right? So if you actually do the estimates, yeah, so if I do the estimates, the I'm doing both, and then this is the trapezoid, and this is the midpoint estimate. The trapezoid is too big. Again, it's still the 2.3025, whatever we're looking for. This is too small, but even with 25 rectangles, it's pretty close. With 100 rectangles, it's actually getting a lot closer. With 1,000 rectangles, we do have 4-digit, or maybe even close to 5-digit accuracy. And with 10,000 rectangles, we definitely have 6-digit accuracy, 302585, right? So we're getting good, they're better estimates too. That's the other thing. Trapezoid and midpoint estimates are better than the left and right. You can just tell there's less area that's missed by the trapezoid and the midpoint, right? I guess that's the other thing I should really say is that the trapezoid, switch the words, should write down is that the trapezoid and midpoint estimates are better than the left and right. And then there's one cool thing we're going to see that's sort of surprising. So notice are better estimates. Left and right. There's a question that gets begged, which is how is the computer doing this? When I give the integrate command to Mathematica and it gives me almost exact value, what is it doing? Because we saw the left and right sums weren't enough. It could be doing a mid or a trapezoid because with 10,000 rectangles or something, because that would give us, well, I just erased it, but that gives us the accuracy I found. But you got to figure that these computer programs are very sophisticated and they're using like harder algorithms that are getting better approximations, right? So we already saw trapezoid and midpoint are a little more complicated, but they give you much better approximations. If you do this plot again, where you have, again, the number of rectangles and then the exact value in the middle, let's see, this is the midpoint estimate, that's the trapezoid estimate coming down. But here's the thing I noticed is that the left-hand axis is like almost all the same. It's very zoomed in, it's very much more zoomed in. So these are actually much closer estimates. And you can define these error terms just like we did with left and right. And if you do this, you see, well, you see something interesting. And I ask a question on the lab handout itself. This is not something you notice with the left and right sums, the errors, but the errors here, if you compare the errors to each other, like this is the trapezoid error for 100 rectangles, this is the midpoint error for 100 rectangles. I feel like something kind of jumps out. Something jump out at you about the relationship to each other? Yeah, like points, the 6.6 is double the 3.3. And even the 3.6 doubled would be 7.2. So it's not exactly half, but it's like about half or double. The one up there is about the one with 25 rectangles. The midpoint error is about half. The trapezoid error, 1,000 rectangles, is it still working? The midpoint error, about half the trapezoid error. 5,000 rectangles, pretty good. 10,000 rectangles, pretty good. Yeah, so this is another big fact. And there is possible to justify why this is happening, but like, it does turn out that there are pretty good reason. There's a good reason. It turns out that for quadratics where you have like a parabola, you can actually prove that the midpoint error is exactly half the trapezoid error. And you can always estimate, just like we estimate with lines, like tangent lines, you can also estimate with parabolas. We'll see that towards the end of the course actually with Taylor series. If I wanted to take like the best parabola estimate, that would give exactly twice the error. The trapezoid would be exactly twice the error. So another fact is that in general, the trapezoid error is approximately twice the midpoint error. And I actually want to look at this for a second because there's this thing called Simpson's rule, which I think is worth talking about. It's not, we're getting into the esoteric stuff a little bit, but a lot of computer programs actually use, there's this thing called Simpson's rule that they use to actually do these estimates, and it gives you really, really good estimates with not nearly as many rectangles. And I claim we can actually see the definition of the Simpson's rule looks kind of random, but in fact, I'll show it to you. It's on the, just a little bit lower. Come on. Yes. 1/3 of the trapezoid sum plus twice the midpoint sum. And when you see this formula in books and stuff, it just looks super random and weird. But I think we can do some math here. So let's say we could think of this. This is really the, right, the trapezoid error is the absolute value of the actual area minus the trap approximation within rectangles, right? And that's a, sorry, pause the share. Glare on the screen the way I have it. Okay, so this is twice the absolute value of the actual area minus the midpoint estimate. We've also seen that they're opposite signs, right? Like one's positive, one's negative, the error, because one's an overestimate, one's an underestimate. So in fact, if I wanted to remove the absolute values, I have to have one of these, like these are both supposed to be positive quantities. Error is always supposed to be like a positive quantity, like you're just measuring an amount. You don't really talk about negative error usually, but that's why we take the absolute value, just to make everything positive. But if mid and trap are on, and by the way, I could also write here just like the integral a to b f of x dx, right? If I wanted, that's what the actual area is. So if I wanted to actually take away the absolute value signs, I could if I kind of flip one of these, because if the actual area is bigger than the trapezoid area, suppose say, then this quantity would be positive, but that would mean the actual area would be less than the midpoint area, so this would be negative. But one way you can do that is you can like swap these two. Does that make sense? What I'm saying? I feel like I'm saying it in a very vague way or something, but right. If C equals the absolute value of let me do this smarter. Yeah, that's what I'm trying to do. So if I had like the absolute value of 4 minus 7, that's 3, right? But 4 minus 7 itself is negative 3. And so if I want to drop the absolute values, I have to actually switch. I have to actually switch these to get the same value. That's all I'm saying. Is that plausible or plausible now? Okay, so what I want to take away the absolute values and say, and I'm actually going to write the integral a to b f of x dx minus the trapezoid estimate is approximately twice, and I'm going to flip this now and make this the midpoint error minus the actual integral, the actual area. Flip because one error is negative. Okay, but now what if I actually solve this equation? This is an approximate, so it's not exact, but what if I solve this equation, if I move things around and isolate the actual area? Okay, so let me do this step by step. This is still this. Let me just give this a name. Let's just call it I, or A. How about A? Let's just call this A. I've written actual area, I've written integral. So let's just say A for actual area. So A minus the trap of N is approximately 2 times the mid minus 2 times the area, right? So what I can do is I can add the 2A over to this side and add the trap over to this side. So that means 3A is approximately trap plus 2 times mid. Which means A, we could divide the 3 over here. And that's exactly what Simpson's rule is. That if this error is very close, if this is very close to being twice the error of this, then I can actually get a different estimate. I can get an almost better estimate. Another way to think about it, maybe, this algebra might look kind of random. Another way to think about it is like, okay, the error from the trapezoid is like, say the trapezoid error is the trapezoid sums a little more than the actual area. So this is a little bit of an overestimate. This is a little bit of an underestimate, but only with like half the error. And so if I double this, then these kind of become equal and opposite sides of the actual area. So that when it's almost like a weighted average. Some people call this a weighted average. But this is the way the math works. And it's kind of cool. This is called Simpson's rule. And it's a great approximation. And in fact, I have some numbers here that I'll show you on the screen. I usually do this in classes anyways. Usually when I have students do the lab longer, they don't get to the Simpson stuff because it's at the very end of the lab. Yeah, it's right there. So if this is the Simpson's rule, and I try it with 1,000 intervals, well, okay, I can actually define the error. Here's the error. Remember, with 10,000 rectangles with the left and right, we were only getting like 3 or 4 digit accuracy. Here with 25 intervals, I get within 0.0000. So that's already like 4 digit accuracy. With 1,000 rectangles, I get 10 to the minus 11th. So I get like 10 digit accuracy. With 10,000 rectangles, I get like 14 digit accuracy. So if I did like, again, just to make this more stark, if I did this with 10,000, oh, you know what'll happen if I do this? It'll actually give me a fraction because it's computing the exact value. It's insane. So let me give, sorry, I need to do like the in command with, let's say, 20 digits. And then let's actually compare that to log 10, natural log of 10. Mathematicus considers mathematicians consider log to be natural log. So there's no like ln command. This actually is the natural logarithm. What? Oh, I said n instead of 10. So you can see actually, look how much these agree. They agree up to there. So that's kind of amazing. Like, this is really, there's a real art to all this numerical integration stuff. Like, you can go really into the weeds with it, because there's lots of real world examples you just can't integrate nicely. And so you have to do these estimates and have computers estimate things for you. And you can go much farther than this, but somehow you're trying to, what I want to say is basically with Simpson's rule, you're trying to cancel out the relative errors of the midpoint and trapezoid rule. And this weighted average cancels those out and gives you like, so all you're left with is like really a higher order error, like that's much, much smaller. Okay, fair. Okay, so there's a lot there, but hopefully, I mean, I think on the homework, I just ask you to like write down mid of 3 and trap 3 or something for, a couple of different examples or something. And it doesn't really go into all this stuff. Oh, I wanted to explain the formula for the midpoint rule though. So we may not get to improper integrals till Wednesday, and then we might, in that case, I might just have you watch one of the 2 videos for Wednesday and watch the other one for the following Monday. I'll have to readjust that. It's good that you watch videos, so please keep your questions about them for Wednesday, and I'll have you watch another one because we can dive in pretty deeply to improper integrals. Let's take a break for a couple minutes and then come back and I'll try to explain the midpoint rule formula, where that comes from. And then maybe we'll call it a day. But let's take a break for a couple minutes and just stretch. There's a lot of numerical integration. Are you happy I walked you through it, or do you wish you could just tell yourself? Okay, good. I did share. Oh, well. Accuracy. Yes.
May I ask you a question?
I suppose.
So sorry for interrupting your break. So like I think it's section 72. I don't have it pulled up, but it says to differentiate the right side of this equation to figure out if like they match or something.
Oh, if it's correct.
Yeah, but then like I just don't I'm like, so should I integrate this and then see if it equals this, or should I, because
Well, they give you this as the answer, right? And they're
Yeah.
asking you whether it's the correct answer.
so like I'm confused on, I if I follow like the instructions they write down, then like they say to differentiate to see if like that
Yeah.
would equal this, but
And does it?
doesn't.
Right, so it's false.
Okay, so
Yeah.
I want to make sure I read it right, because like the way they set it up makes me want to integrate that.
Yeah, and you could, but I mean, I guess it's the idea is you can always check an integral
Yeah.
by differentiating your answer and seeing if you get back what you started with.
That makes sense.
I think that was the whole
Okay, I
reason
just
I
wanna make sure I was-
Yeah, no. I'm also just trying to mess with your heads.
Yeah, I was like, wait, we're integrating. What's going on? Thank you.
Oh wait, who was the one who lost her
I
AirPods?
found
Was that
them.
you? Did you find them? You
Yeah,
found them?
You were right. They're in my bag.
Good,
They're
okay.
in another pocket.
I was worried about it because I was like,
I was gonna tell you that I found them.
like I went home on Friday and I didn't have my AirPods and I was like, I knew I left them at my desk in the office, but I was like,
It's hard because like they're so small.
yeah.
I feel like I'm always losing them. So.
Well, I'm ridiculous. I also have a pair of Power Pros at home. And
Okay.
I like the ear hook. So at home a lot when I'm just relaxing, it's like nice to have them.
The AirPods fall out a lot.
Yeah, I don't have the right ear
Me too.
for, although I actually got different. I got little foam,
Oh, is it like an extra?
like memory foam. You can like order like a little memory phone.
Oh,
like little memory foam things that are,
So much more comfortable.
and so, yeah, and
Okay.
they go in your ear and then they kind of expand and fill in.
Okay, that's.
So on Amazon or something, I found like memory foam attachments for AirPods.
The normal ones kind of hurt my ears after using them for a while.
Yeah, right.
So-
And I don't have the right shape, like they just fall out of my ear, but these kind of stick in because the foam expands.
I'll look into that.
So very important things we're talking about. I have those too. I have Power Beats. I like those. Yeah, I think I bought a new laptop and they had like a get AirPods for either free or AirPod Pros for like $60 or something. So I was like, okay, I'll get some AirPods. So now I have both the Power Beats and AirPods. But no, in general, the ones that go over your ears, like I could wear them like forever, which is dangerous because sometimes I'm at home just like with my Power Beats on doing like whatever and not paying attention. Okay, let's just do this and we can wrap up. So the trapezoid formula I said was just the average of the left and the right, because each trapezoid is the average of the left height and the right height. The midpoint sum is a little more complicated looking. It's on the screen there, but I'll try to give a sense. Let's do an example. Probably the best thing to do. So let's do the midpoint. Let's just do mid 3 with the same functions again. You know, f of x is 1 over x. And a equals 1 and b equals 10, right? So if you did this, where the 1 over x function drops off like this, we go from 1 to 10. And it's really all about the interval again, right? So we know, again, if we break this into 3 pieces, it's 4 and 7. But now what we want are the midpoints of the intervals. So what's the midpoint of the interval from 1 to 4? 2 is halfway between 1 and 4. 2.5, right? 2.5. I definitely didn't draw these the same width. What is this, 5.5? And this is 8.5. Is that the halfway point? Between 7 and 10, between 4 and 7. Okay, so those are the heights we're going to use to draw our rectangles. So it's going to be this height. I'll draw a different color. So that's a rectangle, that's a rectangle, and then this one through this point. So these are the points we're using to get the heights of our rectangles, right? And so the Riemann sum would be, so mid-3 if we wrote it out, x is still 1/x. Mid-3 would be 1/2.5. That would be the height. I'm not even going to simplify that to like 1/5 is 2/5. I don't really care. I really care about the pattern times 3 plus 1/5.5 times 3 plus 1/8.5 times 3, right? So those are just the heights. It's like f of, and really the 1/2.5 is just f of 2.5. I can write it as f of 2.5. Let me try to make this even more explicit, like our delta x or delta t or whatever. Actually, let me label these points down here. This is like t sub 0, right? This is t sub 1. This is t sub 2. This is t sub 3. The distance between successive t's is the delta t, right? Okay. But we're doing the midpoints. So we're not going, like one way to think about this, let me rewrite this again. This is f of 2.5 times 3 plus f of 5.5 times 3 plus f of 8.5 times 3. This 2.5 is really like 1. Just think about how we set these things up. It's 1 plus 1.5, right? Because that's half of the delta t. This is 4 plus 1.5. We were just trying to think about how we came up with these. I'm just trying to get a pattern. Right, that's how we found those points. We just added half of the, our delta t is 3. We just added half of it. So, okay, if I really tease this out, this is like our starting point A. And here we're adding like half of a delta t. I could call this, maybe I should say T0. This right here is our T1 plus half of delta t. And this is our T2 plus half of delta t. Did I label these correctly? Yeah, okay. I'm trying to get something that's going to look like that. What is, how is T1 related to T0? How do we get from T0 to T1? What do we add to T0? A delta t. So this is actually, I'm just trying to like tease this out as much as I can. So this is actually T0 plus delta t plus 1/2 delta t. T2, just to make this clear, this is that. T2 is how many delta t's over from T0? 2. It's 2 delta t's over, right? So this is actually T0 plus 2 delta t plus 1/2 delta t. So now we're starting to see something. This is T0 plus 1/2 delta t. Remember, T0 is just A, it's our starting point. T0 is our starting point A. This is A plus 1.5 delta t's, 3/2 delta t. And this is A plus 2.5 delta t's, which is 5/2 delta t's. And it sort of makes sense if you think about how we broke this interval up. Like there's 3 rectangles, but there's like 6 little half intervals now, right? There's 6 little half delta t's. And we want the first, the third, and the fifth one. We want the odd number of delta t's. That's kind of how we're building this. And so maybe you can start to see, I mean, I'll do it more explicitly, but like b minus a over n is the delta t. 2i minus 1 is actually pretty good for encoding odd numbers. 2 times 1 minus 1, 2 times 2 minus 1, 2 times 3 minus 1. That's going to be a nice thing to know. Let me words and write this. So, okay, let me write this one more time, just to give it as the final version. It's like, yeah, it's the odd multiples of 1/2 delta t is really what we're trying to get the midpoints of each subinterval. We're doing the odd, we're taking an odd number of halves to get to the midpoint, to get to the halfway point of each interval. Does that make some sense? Please ask questions, interrupt. So again, just to make this super, this is f of a plus 1/2 delta t times delta t. That's what the 3 is up there, right? Plus f of a plus, you don't even do it this way, 3 times 1/2 delta t times delta t plus f of a plus 5 times 1/2 delta t times delta t. So it's the odd multiples of 1/2 delta t. That's what we're trying to encode. And if you think about turning this into summation notation, so odd numbers, I mean, think about how even numbers are encoded. So 2, 4, 6, 8, into 0, 8, etc. That's actually like 2i from I equals 0. You know, that's a good way to encode evens. 2i. And you can encode odds with 2i plus 1 or 2i minus 1. Because you're basically taking the evens and shifting them by 1. 3, 5, 7, 9, etc. So I'm saying that's a good way to encode that is 2i minus 1 if you want to start from 0. Nope, if you want to start from 1. What does that do? That starts from 1. So there's a little bit of 0 to n versus 1, 0 to n minus 1 versus 1 to n stuff going on here. I just realized should have been more careful a little bit. Well, I might actually do a slightly different formula that's going to turn out to be the same formula. It's more natural for what we just did. So I'm going to say 2i plus 1 actually. If I start from 0, I start plugging in I equals 0, I equals 1, I equals 2, I get the odd numbers, right? Okay, so if you do that here, then you can think of this as the sum from 0 to 2 of f of a plus 2i plus 1 times 1/2 delta t times delta t. So I kept rewriting that and rewriting that and rewriting that until it looks like something I could encode into summation notation. So actually, yeah, I really would have preferred to go from, I should have written, I could reorient all this and have done like, yeah, I could have counted slightly differently and had it look exactly like the formula on the screen. But I think this is fine. So in general, you're just going to do the same thing. You're just going to go, you're going to count the odd multiples of 1/2 delta t. That's what you're going to add to your starting left endpoint. And those numbers you're going to plug in to get the heights. of your rectangles. So in general, mid n is by definition the sum from 0 to n minus 1 f of a plus, it's the same formula. The half delta t. And that's the height of your rectangle, and this is the base delta t. It's always f of something times delta t. It's just a question of what the things are that go in that you're plugging in, right? Okay. So that's kind of ugly, but I mean, hopefully it's at least somewhat plausible from the example that we, and that's what you're doing. You're just counting, instead of breaking the interval up into delta t's, you're breaking it up into half delta t's because those are the points you want to land on. Okay, cool. Any questions? Yeah, I claim if I change that to 0 to n minus 1 and change the 2i minus 1 to 2i plus 1, it would be the exact same sum. It may not be super obvious, but I claim that that's true. All right. Actually, while the improper integral stuff's fresh in your head, was there anything from the videos that really like bothered anyone that wants to talk about, like questions that was like, as long as we're here, and you just watched those? Let me pull up the. So, okay, just as a last thing, I'll just say, like, I'm gonna go. So what I'll do is, you've already submitted notes on these two. I think I'll have you watch the first one of these two, the first one of the third, and just the third video, not the fourth one, because I don't think we'll get to the fourth video, I mean, the comparisons until next Monday. So I'll have you guys just watch the third video, but it's kind of another important type of improper. There's basically two types of improper integrals, whether you integrate all the way to infinity, so your interval becomes infinitely wide, or whether your function blows up to infinity somewhere, like you try to integrate across a vertical asymptote. Basically a horizontal asymptote or a vertical asymptote. Those are the two types of improper integrals. So I'll try to change this, but for Wednesday, just watch the third video and I'll push this off till next Monday. Cool. All right, we can call it a day a little early. I'm happy to answer questions.